Hello, and welcome to the second part of the 555 timer operation module. In this module, we'll be going over in a little bit more detail the operation of the one-shot module. This was covered in class, but we'll go over it again just in case some people missed it. So at this point, we've already determined exactly how our trigger circuit works. Additionally, we know how our low-pass filter works, and we know how our motor works. So all that's really left is to find out how our one-shot turns our trigger pulses into our output pulses. Now if we look at the inside of the 555 just a little bit closer, we can recall that our trigger pulse looks like this simply falling edge which then rises again. Internally to the 555 timer, this lower comparator compares our trigger pulse to a voltage of 1/3 VCC. That's about this level here, in order to generate the set pulse for our internal SR flip-flop. And so as soon as trigger drops low, this set pulse goes high, and we end up setting our RS flip-flop, which makes Q go high and Q naught go low. So as soon as we set, Q goes high, Q naught goes low. Now, if we just know that happens, we can take a look at how the rest of the circuit functions. Here again, up in the top, we have our trigger pulse. And we can see that if trigger goes high, right here, it's going to send Q high, Q naught's going to go low. As soon as Q naught goes low, that's going to force this node low, which is going to turn off our switch. So the switch is going to turn off, which allows C2 to be charged through R2 up to some voltage. Now as soon as C2 charges high enough, it's going to flip this comparator, send reset high, which is going to force output low, it's going to force Q naught high. Once Q naught goes high, this switch is going to turn into a short circuit and it's going to short C2. So let's just draw out some of these waveforms. Now when we start, Q naught is sitting high. We're assuming at some point we had a recess signal, and so Q naught is sitting high. Additionally, the voltage across our cap or our discharge node and our threshold node is sitting at low, because since Q is high, this switch is on, and so C2 is being shorted to ground. And we know that our reset signal is low. We can tell that because this node here is at 0 volts, meaning that the positive is lower than the negative on this comparator, meaning that reset's sitting at 0 volts. Now as soon as we get a trigger pulse right here, as soon as we have a set pulse, remember Q naught is going to drop low, so Q naught drops low. And Q naught's going to stay that way for a while, so we know Q naught's going to be low. As soon as that drops low, we turn this switch off, right? This node has just dropped low, which turns this switch off. And now C2 can begin to charge through R2. So C2 is going to charge up in some sort of an exponential fashion here. It's just going to start increasing. And reset is still low, nothing's changed there. Now as soon as the voltage on C2, or the voltage right here, passes 2/3 of VCC, you can see that reset's going to shoot high. So really, as soon as we get to 2/3 VCC, reset is going to pulse high. Now when reset pulses high, Q naught's going to increase, and so Q naught has now jumped up. As soon as Q naught jumps up, this switch turns on, which is going to short this voltage right here. It's going to drop back down and sit at 0, and as soon as that voltage drops down, reset drops low again. And so we really only have a little pulse of reset. We had our C2 rising and then dropping down when it hit 2/3 VCC, and Q naught was low during this rising portion here, so these things are time aligned, and then went back high as soon as this voltage dropped low again. And so that's what our waveform looks like here. Then it's going to repeat the next cycle. Q0 drops low on the rising edge of our set pulse. We begin to charge C2 on that rising edge, and reset stays low until we hit 2/3 VCC, when reset pulses and forces that voltage back down again. So that's how this circuit implements a one-shot, and our output is then going to be the inverse of Q bar, meaning that this time here is going to be our T on. That's the time we'd like to solve for. So as this circuit transitions through these states, there's really only two different equivalent circuits we need to be concerned about. The first one is what happens during this first time and this second time period here, and that's this first equivalent circuit here. During this portion of time, Q0 is high, as we can see, and because Q0 is high, this switch is on, and so C2 is shorted, and you can see that here, C2 shorted. Now during this period of time, nothing very interesting happens. We're simply running our 5 volts through R2 to ground. C2 is not charging. This node right here, corresponding to this node, is stuck at 0 volts. The more interesting time period is this second period right here between these two red lines, where we're actually charging our capacitor and waiting for it to hit 2/3 VCC. During this period of time, Q0's low. If Q0's low, that means that this switch is an open circuit, as you can see in this second equivalent. So what we need to solve is the time it takes this second equivalent circuit to charge C2's voltage from 0 to 2/3 of VCC. It's a very similar process to determining our trigger time. So to start out solving this, we can write our node equations. And here we have one current coming in this way and a current leaving this way. We're solving for this voltage right here. So we'll get 5 volts minus VC2 over R2. And this is going to equal C dVC2 dt. Now we can multiply through by R2 and rearrange. We're going to get R2C dVC2 dt plus VC2 equals 5 volts. And this equation is very similar to the one we got when solving for T-trigger. In fact, it's the same equation, and so we immediately know what the solution is going to be. We're going to end up with VC2 of T equals 5 times 1 minus e to the minus t over R2 C2. So that's our equation for VC2, but what we're really interested in is at what point in time does VC2 equal 2/3 VCC. So we want to know when this happens, because as soon as it hits there, that's going to set our T on pulse length. So beginning from our solution in the last slide, we can solve this again, and now what we're really concerned with, 2/3 VCC equals VCC 1 minus e to the minus T on, because at T on we get this, over R2 C2. Now at this point we can simply cancel our VCCs, and we can throw a 1 onto the other side, so we'll subtract 1 from both sides. We're going to have minus 1/3 equals minus e to the T on over R2 C2. Let's make both sides positive. Now we can flip both sides upside down so that we have 3 equals e to the positive T on over R2 C2. Take the logarithm of both sides and multiply through by R2 C2. Means that we know now that T on is going to equal R2 C2 times the natural log of 3. And we can use this equation to solve for T on. Remember, we need T on to be about 90% or so of our minimum encoder period, which happens at our maximum encoder frequency. Once we've solved for R2 C2 in that fashion, we now know how to select every component value seen here. Remember, R1C1 was selected to ensure that our trigger pulse was 1 to 10 microseconds, something in that range. We then select R2C2 in order to ensure that our one-shot outputs a pulse of about 90% of our minimum encoder period. And then we selected R3C3 in order to filter the output PWM to get a fairly constant speed. It'll have some ripple on the top. And once we've solved for that, that's really the last set of components that we need and able to get this circuit to function properly and how we'd like.